Hello everyone, I am Peng Long from the University of Science and Technology of China. Today, I'm going to talk about a paper titled Decoupling and Aggregating for Image Exposure Correction. The images captured under improper exposure conditions often suffer from contrast degradation and detail distortion. Contrast degradation will destroy the statistical properties of low-frequency components, while detail distortion will disturb the structural properties of high-frequency components, leading to the low and high-frequency components being mixed and inseparable. This will limit the statistical and structural modeling capacity for exposure correction. To address this issue, this paper proposes to decouple the contrast enhancement and detail restoration within each convolution. We devise a contrast-aware and detail-aware unit to facilitate the statistical and structural regularities modeling. The proposed units can be plugged into existing CNN-based exposure correction networks to substitute the traditional convolution to improve the performance. Furthermore, to maintain the computational costs without changing, we aggregate them into a single traditional convolution kernel. Images captured under improper exposure conditions often suffer from underexposure or overexposure problems, as shown on the left. Image exposure errors can occur due to several factors: errors in measurements of through-the-lens metering, hard lighting conditions, dramatic changes in the brightness level of the scene, and errors made by users in the manual mode. The under- and overexposure images often suffer from contrast degradation and detail distortion. Contrast degradation will destroy the statistical properties of low-frequency components. Detail distortion will disturb the structural properties of high-frequency components. As shown in the figure, we use the image Laplacian pyramid to decompose the overexposed image and the normally exposed image to low and high frequencies. Then, we substitute the low and high frequencies of the normally exposed images into the overexposed images, respectively. As you can see, by replacing level n, the low-frequency part, with the overexposed image, the resulting image still has the detail distortion problem. Similarly, when the other levels, the high-frequency parts, are replaced with the overexposed images, there is still the contrast degradation problem in the generated images. To achieve better contrast enhancement and detail restoration, some researchers propose to decompose and restore the input image's lightness and structure components, respectively, to 2041. For example, some researchers decompose images into illumination and reflectance components by utilizing rednecks theory and then design a specific network for each component, 19, 20, 24. Other researchers propose to decompose the input image into multi-scale components and adopt the coarse-to-fine strategy to progressively recover the lightness and fine-scale structures, too. However, the decomposition operation inevitably destroys the relationship between brightness and detail and cannot balance the contrast and detail enhancement, leading to oversmooth problems or artifacts for enhanced results. To address the above issues, this paper proposes to decouple the contrast enhancement and detail restoration during the convolution process. This method is based on statistical observations that the feature response in local regions can be decomposed into low-frequency components and high-frequency components by a difference operation. Based on this, we introduce a novel contrast-aware (CA) unit in parallel with a detail-aware (DA) unit to guide the contrast and detail modeling, termed Decoupling-and-Aggregating Convolution, DACONV. Different from TCONV, we inject the addition/difference operation into the convolution process, which can guide the contrast and detail modeling in an explicit manner. Furthermore, to balance the contrast enhancement and detail restoration, we introduce a dynamic coefficient for each branch to adjust the amplitude of the feature response. Our proposed DACONV can be used as a general unit to substitute the TCONV kernel in existing CNN-based exposure correction networks to facilitate contrast enhancement and detail restoration. To reduce the computational costs, the CA, DA, and dynamic coefficients are aggregated into a single TCONV kernel by structural reparameterization in the inference phase. The aggregation is conducted before the activation function, and the linear superposition can reduce computational costs without changing the function of DACONV. After that, the performance of networks can be significantly improved without introducing extra computational costs compared with the original network. Evaluations of 9 methods and 5 benchmark datasets demonstrate the effectiveness of our proposed method, as shown in Fig. We report the PSNR/SSIM performance of 9 exposure correction methods on the ME dataset and SICE dataset. We report the PSNR/SSIM performance of 6 methods on public LOLv1, LOLv2 real, and LOLv2 synthetic datasets. We can observe that the performance of most of these methods is comprehensively improved after utilizing the DACONV, demonstrating that our proposed DC is robust and can be embedded in various network architectures. It is worth mentioning that unsupervised algorithms, such as 0DCE11 and RUAS20, are also improved after using DACONV, indicating that DACONV is not sensitive to network learning methods. This figure shows the visual comparison before and after using DACONV on underexposure images of the SICE dataset. We can observe that the TCONV-based method suffers from blurred details and color distortion, especially in the red box, while the DACONV-based method is better at detail restoration and contrast enhancement. To verify that DACONV can capture the image details and contrast relevant information explicitly, we select overexposure and underexposure images in the same scene and visualize the feature maps of CA and DA in DACONV, respectively. For underexposure images, CA can perceive the brightness distribution and pays more attention to dark areas, while DA focuses on extracting structural features. For overexposure images, CA pays more attention to the overexposed area. Thank you for your attention. I'm happy to answer any questions you may have.